Uncomputability in information theory. This is Claude Shannon, widely regarded as the father of information theory. In the 1940s, telecommunication systems were relatively young, and the engineers working on those systems were trying to optimize the signal-to-noise ratio of the signals they were transmitting over these systems. For telephone lines, they were trying to make the voice on the receiving end as clear as possible. And from their attempts, they knew that there was a trade-off between the clarity of the sound and the consumed bandwidth, because over the extra bandwidth, they could send redundant information to make up for the information that was lost or distorted along the way. But they didn't know whether this extra bandwidth was really needed or whether they were just not using the available bandwidth in the most efficient way. And they did not have a precise mathematical formula or theory to tell them what the maximum possible signal-to-noise ratio was given a certain bandwidth. And that's when Claude Shannon came along. He said, okay, suppose we fixed the bandwidth. This gives us a channel with a certain amount of noise that we know. Let's try to find a precise mathematical formula for the maximum information rate, let's call the capacity, that we can transmit over these channels. And this thinking led to this famous paper, which included this expression. The engineers could now come to Shannon and say, given this bandwidth, what is the maximum signal-to-noise ratio that we should expect to be able to achieve? And Shannon would say, here, if you substitute by your channel in this formula here, you will know what the maximum signal-to-noise ratio is. And the engineers rejoiced, not only because they had an expression for capacity, but also because the expression was computable. And by computable, I mean there's an algorithm, a systematic way to get a number out of that expression. And this is not always the case. So there are mathematical expressions for which there cannot exist a systematic way to compute their value. Such expressions are then called uncomputable or undecidable. Perhaps the most famous undecidable problem is called Turing's halting problem, which was introduced by Alan Turing, widely regarded as the father of computer science, in 1936. And I'm not going to explain what the halting problem is, but I'm going to explain one of its variants called post-correspondence problem. And it goes like this. So UI here is a word, a string of symbols from some finite alphabet. If the alphabet is binary, for example, this is just a string of zeros and ones. VI here is another word. Together they form a word pair. So you have K of these word pairs. The PCP question is then, is there a way to arrange the pairs with repetitions allowed such that eventually the two strings you form are equal? And it turns out that amazingly, if you have 6 or more pairs of these words, there does not exist an algorithm that will tell you whether this match will happen. Your only option is to keep going forever until you find a match, or don't find a match. In more technical words, this problem is undecidable for 6 or more pairs of words. And that's why it was nice when the expression that Shannon discovered turned out to be computable, because the engineers could use it in building these telecommunication systems. They had numerical values to work with. But there was a caveat.